Today we're going to be talking about electron configuration. Now, electron configuration is a way to kind of draw an atom but in word form. But what it really is what is the distribution of electrons inside of an atom? Now, we've always been shown that electrons are moving around the nucleus in a circular pattern, but that's not actually what's happening. We use the Bohr model of the atom to explain electrons because that's the easiest way to show where electrons exist. But electrons actually exist in pockets around the atom and around the nucleus in places we call orbitals. Okay? So, for example, this is an artist's rendition of what neon actually looks like on the inside of an atom. Neon has 10 electrons, but it's not just 10 electrons going around the middle like planets around the sun. There's actually all these pockets around in these little sections inside the atom itself. We've got a couple of spheres here. We've got a couple of these dumbbell shapes. And the electrons are existing in pairs in those sections. Okay? So, how do we know this? Well, we know it because we've been able to take some pictures of it. Okay, so these are different atoms with different shapes. This atom is a small atom with one sphere. This atom has two spheres, the middle and the outer. This one has three, middle, outer, and then an even further outer shell. Here is that one of those dumbbell shapes, those figure eight shapes. And then here is a figure eight shape inside of a sphere, and then a figure eight shape outside of the sphere. And then this one has two figure eight shapes on either side of the nucleus. And these sections we call orbitals. Okay, so what these sections are subgroups that we call S, P, D, and F. The S subgroup is that sphere. The P subgroup are these dumbbell shapes. Okay, they exist in an XYZ plane. All right, so one dumbbell will be in the X, one dumbbell will be in the Y, and one dumbbell will be in the Z. The D subgroup has two dumbbells inside each plane, and we actually have 5 different planes of where the D subgroup will be. I should say 5 different shapes inside the XYZ plane. The fifth shape being a very odd dumbbell with a strange circular disc around it. So each one of these places is somewhere where an electron will exist. Okay. Now there's actually a 4th subgroup called the F subgroup, and it has 7 different shapes. So think of the F subgroup as being 2 of the D's put inside of a plane. Okay, so it has multiple places for the electrons to exist. Okay, so the S subgroup has 1 shape, the P subgroup has 3 shapes, the D subgroup has 5 shapes, and the F subgroup, that last one, has 7 shapes. Okay, so where do they exist? You've got your periods and your rows and your columns and your families. And the first place we're going to talk about are the S subgroup atoms. So all of the atoms in the alkaline earth and the alkali metals are considered part of the S subgroup. Okay, the P subgroup is going to be columns 13 through 17, or I'm sorry, 13 through 18. The noble gases are included in this. The D subgroup are going to be all of our transition metals. And the F subgroup is going to be our rare earth elements. Okay, and the last one, helium, up here is going to be part of the S subgroup as well. Okay, now to remember those shapes, S subgroup can hold up to 2 electrons. It only has 1 shape. The P subgroup can hold up to 6 electrons, which is 3 shapes. D subgroup can hold up to 10 electrons across. That's 5 shapes. The F subgroup can hold up to 14 electrons across. That's 7 shapes. Okay. Now, how we draw these is with a series of numbers and letters in order to represent where the electrons exist inside of an atom. So we have the first number, which represents the energy level. Now, it doesn't necessarily mean the period, it just means the energy level of the orbital, the s, p, d, or f. The second number, the exponent, is going to represent the number of valence electrons, and the letter is going to represent that shape, the s, p, d, or f. Okay, so this particular element, which is represented by 1s1, is going to be in the 1s1 space, which is hydrogen. Okay, now there are three things that we talk about when we deal with electron configuration, and that's Aufbau principle, Hund's rule, and the Pauli exclusion principle. Now, Pauli exclusion and Hund's rule we're going to talk more about next class when we're dealing with other types of notation. But today we're going to talk a lot about the Aufbau principle. The Aufbau principle states that electrons must fill orbitals with lowest energy first. So you never just jump to the end, you always fill in order. So this is a graphic representation of what the Aufbau principle is. So if you remember, I said that S starts with 1, P starts with 2, D starts with 3, F starts with 4. You've got your 1, 2, 3, 4, S, P, D, F. It doesn't read left to right like a normal book, okay? It reads actually in these diagonals. So this is the order of energy according to the Aufbau principle. And down here, all of these arrows are put in sequence. 1s2, 2s2, 2p6, 3s2, 3p6, etc. Now, if this becomes a little difficult to remember, well, you can actually just remember the periodic table too. So the periodic table does read left to right. 1s2, there's 2 spaces. 2s2, 2p6, p starts with 2, remember? 3s2, 3p6, there are 6 spaces. 4s2, 3d, there are 10 spaces. Remember, D starts with 3. Even though it's on the 4th period, it starts with 3. Okay, so this is the Aufbau principle. Okay, it's just written in a different order than what you're used to seeing. Okay, but the periodic table is in left to right. Okay, so make sure that you know this order. All right, so let's do a couple of examples. Lithium. Lithium is in the 2nd period. It has an atomic number of 3. So if it's in the 2nd period, that means it has 2 layers. It has 2 shells. It's in group number 1, which means that it has 1 valence electron. Okay, lithium is in the S subshell. Okay, it's in the S block, and it has an electron configuration of 1s2, 2s1. Now, it is the 2s1 block. But when you write electron configurations, you must always start at the beginning and finish on whichever element that you have. Okay, let's look at boron. Boron is the 5th element, atomic number 5, and it's in the 2nd row, so that means it has 2 subshells again. It's in group 13, group 3, so that means it has 3 valence electrons, and it is in the P subblock. All right, it ends with 2p1. All right, so you have to start at the beginning. 1s1, 1s2, 2s1, 2s2, 2p1. But here it doesn't write 1s1 or 2s1. It only writes the end of the row. So you don't have to write all of the ones in between. For example, if I were to do oxygen, oxygen ends on 2p4. So your electron configuration of oxygen would be 1s2, 2s2, 2p4. You wouldn't write all those ones in the middle, 2p1, 2p2, 2p3, 2p4. Okay. Some of the ones to remember, whenever you get to right here, this starts 3d. And the tricky one is the F block. Remember, this section of the periodic table goes right here in the real periodic table. So it's important to remember that that's going to fit into that section. So when you get to 6s2, you go immediately into 4f14, which is what that graph shows us at the bottom here of 6s2 straight into 4f14. Okay? Right here on the real periodic table. So it's important to remember that that section, the rare earth elements, fits into the middle here. So we will go straight from 6s2 into 4f14. Okay? So, and that's what's depicted in our alpha-val principle of 6s2, 4f14. Okay? It goes straight into that line of subshells. All right, that's about it. Next class we're going to talk more about configuration with orbital notation and noble gas configuration, and we'll use the Hund's rule and Pauli exclusion principle in more detail then. Okay, until then, work together, help each other, and make the world a better place. See ya.